Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We'll continue with our first module on statistical inference, which is our module 2. Today is the last talk of this module. This will address the asymptotic properties of point estimation. Now, what is asymptotic property? So, the understanding behind this is the following. Since if your sample is as big as the population, after all, or in this whole game of inference, you're trying to infer about a population based on a sample, and remember, population is everything that can be measured and sample is some specific measurement that has been done. So, you're trying to predict about population based on sample. If your sample is very big, it's almost as big as the population, your prediction is expected to be very good. For example, if you measured the whole population, then there is no randomness, you have measured everything. But let's say if you have measured half the population versus you measured 1% of the population, 100th of the population, 100th of the population, or 1% of the population versus 50% or the half of the population. You expect when you have measured 50%, your prediction should be better. That's the philosophy behind asymptotics. Now, what people study for a class of predictors or estimator, if you keep making, remember all the estimation recipes we learned so far, maximum likelihood or method of movement, it just takes in the sample size to be something general. You, for a general sample of size x1, x2, xn, you predict. Let's say for the simplest case where you are trying to predict the population mean in terms of sample mean, you take n as x1 plus x2 plus xn over n. So, that works for every n. Now, the guess is that, like, if this n gets bigger and bigger, the predictor should become better. So, this is the theme of asymptotics. So, we start with asymptotics with the notion of consistency. So, like asymptotics is a very big topic. I mean, like, one can give you a full course on statistics just on asymptotics, not just any course, an advanced statistics course is needed to address every aspect of asymptotics. We will just give you a glimpse in this lecture. So, generally speaking, in the estimation, we want estimators that are closer to the true parameter as sample size increases. So, like, if sample size increasing doesn't make it better, then there is something inherently flawed about the estimator, because collecting more data is expected to, that if you are getting better idea about the population, if you are getting a bigger picture, still your predictor doesn't improve, then there is something problematic with the predictor. That's the underlying philosophy. So, it's supposed to be as n goes bigger, the estimated value should be more tightly clustered around the actual value. So, this is what the nature of consistency, this is what consistency tries to capture. A consistent estimator converges in probability, this is what we will capture, we will talk about, and consistent estimator converges in probability to the true value as n goes to infinity. Just to give you an example, our good old friend sample mean as estimator of population mean. So, suppose x1, x2, xn is an IID random sample from a population x with mean mu and variance sigma square. Note that, I mean, now we are making an assumption on variance also. We want them to be numbers, mu finite, variance finite, to avoid all the calculational issues, dividing by infinity, etc. We want it for this setup, where expected value of each random variable is mu and the variance is sigma square. Now, define sample mean. We know that expected value of sample mean is mu, but what is the variance of sample mean? Variance of sample mean is summation xi, the variance of summation xi over n. Recall that variance of summation Cixi is nothing but Ci square variance xi if x1, x2, xn independent. Basically, there are no covariance term. no covariance. So this is what we are trying to achieve. But now if you have this, because these are IID and with variance sigma square, each of these things will have, so this will, so if you plug this formula here, this will be 1 over n square summation variance xi, which will be equal to 1 over n square sigma square. This will give you sigma square over sigma square divided by n. Now this sigma square divided by n is quite interesting. This tells you as n goes to infinity, sigma square over n, I mean it is sigma square over n, so as n goes to infinity and sigma square is something finite number, variance goes to 0, variance of x bar goes to 0. So imagine what's happening. You are collecting larger and larger sample and taking sample mean as an estimator of the population mean. X bar is a random variable which has center same as the population center. If you are taking larger and larger sample, the x bar has less variance. Now, if you think about the distribution as a cloud for x bar, as n goes to infinity, the center remains same as the population center. This, as n goes to infinity, this cloud keeps getting smaller and smaller. So in particular, you can, in the ideal situation, you can imagine, so now let me erase all this and draw the picture. So this is your population cloud. So let me draw the population cloud, and so suppose, well, this need not be circle, but let me draw it with a circle. Okay. So this is suppose population. Now if you take, let's say, sample for, this is, let's say 3-4, just to give a number, same number 3-4 population as a sample of size 100, let's say. If you take sample of size 1000, it will still be centered around 3-4, but the cloud will be, oops, looks bad, my drawing skills are bad, sorry. It's a smaller circle, still centered at 3-4, sample of size 1000. If you take sample of size million, it will just be 10 or lakh or million, whatever. It's still same, a very big sample, so 10 to the power 10. It will look almost clustered around this point. It will still be same picture, it will still have same center, as population, more sample size implies tighter around center. So the fact that now, after all, because your sample is random, when you are doing an estimation based on sample, that's a random object. Unbiasedness and all these properties that we studied saw that, you know, at least under normal population, the sample mean was unbiased, maximum likelihood MLE, MME for population mean. In general also we saw always sample mean is unbiased estimated for population mean. That is, sample mean has the random variable sample mean had same center as the population. Now this calculation, simple calculation, shows us that if you make sample size larger and larger, the sample variance starts getting closer and closer to 0. That is, the sample mean, not sample variance, sorry. If you make the population larger and larger, the variance of the sample mean becomes closer and closer to 0. So in particular, that means that sample mean as a random variable essentially becomes a single point distribution, which is same as the population mean. So sample mean as mu goes as n goes to infinity hits the population mean at target with probability nearly 1. That's why sample mean is a very good estimator of population mean in terms of this asymptotic property. So this is, in this section we will introduce you to, this lecture will introduce you to this kind of behavior. So this is what is very desirable property for any estimator, that is, as you take bigger and bigger sample, it gets better and better in some sense. So a consistent estimator, a sequence of estimator, that is, you have an estimation scheme such that you keep collecting sample of various size. For each size gives you an estimator. When you are taking sample mean, each size gives you, so a sample of size n gives you a particular estimator based on that sample size. So for example, if you are a sequence of estimator, this is generating a sequence for every, because a sequence is what? It's a number for every n. So if you have a sample size n, that will give you a number. If you have a sample size 2n, that will give you a number, and so on. So a sequence of estimator is said to be a consistent estimator or weakly consistent estimator if Tn converges to theta in probability, which means for any number epsilon, positive number epsilon, as n goes to infinity, probability of Tn being in the theta neighborhood, epsilon neighborhood of theta. So Tn is trying to estimate theta. So if you take the epsilon neighborhood of theta, which means this interval, so probability of Tn probability that Tn belongs to this interval goes to 1 as n goes to infinity. So that means for large n, Tn's for very large n with very high probability lies in this interval for all epsilon. So you can choose epsilon as small as you want. You can choose epsilon to be 10 to the power minus 1 million, 10 to the power minus 1000 million. You can still get a large enough n, so such that it belongs to this small interval around theta. So if this is your theta, you can choose epsilon as small as you want. This is your, if you have seen epsilon delta definition of limit in calculus, this is what we are discussing. You choose epsilon as small as you want. So this is your theta. You can keep taking as small interval as you want, any interval around theta. You can choose epsilon as small as you want. You can choose n large enough such that Tn will always be inside this interval with very high probability. So if this is satisfied, then this sequence of estimator is called a consistent or weakly consistent estimator. So basically, formally speaking, this is equivalent to saying for every epsilon greater than 0 and mu greater than 0, there exists some m such that for n greater than equal to m, for all n greater than equal to m, this is bigger than 1 minus nu. So 1 minus nu, you can choose nu as small as you can. So you can always make it as close to this probability as close to 1 as you can. So now we discuss some theoretical results. So as we discussed consistency, we will discuss some theoretical result which gives a sufficient condition for consistency. So now that we have studied consistency and we sort of we sort of defined consistency as a desirable property of a collection of estimators. Now imagine, so remember one thing, we are talking about a sequence of estimators. This is consistent if something happens, consistent estimator of theta, if something happens, something good happens as n goes to infinity. This is a mathematical model for some estimator defined using a sample, and we want to say as sample size n becomes larger and larger, this estimator gets better and better. So, in some sense a sample of size n will give you an estimator Tn, sample of size 2n will give you an estimator T2n, a sample size of n plus 1000 will give you an estimator Tn plus 1000, a sample of size 1 will give you an estimator T1. This n, generally speaking, is introduced to model sample size. So, generally speaking, what consistency is essentially trying to capture, that as the sample size gets better, bigger and bigger, things gets better and better for our estimator. It starts behaving better and better. So, this is now in this section we give you, in this slide we give you an give you some sufficient condition for consistency. If this is a sequence of estimator, then it will be a consistent estimator for theta. If the Tn is asymptotically unbiased or simply unbiased estimator. Formally speaking, it means expected value of Tn goes to theta as n goes to infinity. Of course, if you already have all Tn's to be unbiased estimator of theta, nothing like it. For example, for sample mean, for any n, and suppose your theta is population mean and xn is and you have for Tn to be sample mean of a sample of size n, then always expected value of Tn will be theta. But in general, if it's an estimator such that at least the expected value asymptotically becomes equal to theta, that's one condition that is required for that's one condition that will be important for getting consistency. And secondly, the variance of the estimator decreases with increase in the population size. That is, it should go to 0, decreases to 0 as n goes to infinity. If you have these two conditions, that is asymptotically the expected value of the estimator becomes theta and the asymptotically the variance of the estimator becomes 0, then Tn will be an consistent estimator of theta. Remember, this is only a sufficient condition, need not be necessary condition. So, for example, if expected value of your Tn is, if your Tn is x1, x2, x1 plus x2 plus x3, xn divided by n, we observed, and theta equal to population mean, then expected value of Tn becomes, it is theta, and variance of Tn we just saw is, and sigma square is population variance. We observe that this is equal to sigma square over n, so this goes to 0. So, this will be enough. So, this is consistent. This condition also guarantees that this will be a consistent estimator. As we discussed, sample mean is a consistent estimator of population mean. From that result, we can also kind of give a more slightly general result. So, here we are taking, of course, sample from a population which has mean mu and variance sigma square. We can give a direct proof instead of invoking that sufficient condition. You can see for every epsilon, you can basically take x bar minus mu is less than equal to sigma. The probability of this is equivalent to divided by sigma over square root n, and this quantity, because it is essentially you are dividing this side by sigma over square root n, you divide this side by sigma over square root n, then something interesting happens. There is something called central limit theorem, which we will come soon. This will say this is approximately standard normal distribution for large values of n. I just wanted to, of course, this immediately follows from what we discussed in the previous slide before this slide. I mean, this thing follows also from here, applying this, but I just wanted to bring the central limit theorem angle here, because this is anyway going to be very important in the asymptotics and some subsequent properties. So basically, if you have x1, x2, xn, IID with mean, the same setup, mu and variance sigma square, both finite, there is something called central limit theorem, which says, and this is one of the most foundational theorem in asymptotics, that if you take x bar, which is x1 dot 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 plus xn mod n, x bar goes asymptotically normal 0 1, well, not x bar, but x bar minus mu over sigma n is asymptotically normal 0 1. Well, basically asymptotically, and so this is as n goes to infinity. So in general also x bar asymptotically mu sigma square as n goes to infinity, and z follows a normal mu sigma square implies z minus mu over sigma, sigma square n follows normal 0 1. So this is what, and you know that the variance of, if you know that the, for sample mean, we know that the variance of the sample mean in general also, if the population has variance, we sigma, we just saw sample mean has variance sigma over n, and expected value, as we keep talking, mu. So basically what it says, central limit theorem, you take the sample mean of this population, it is normal. If it is normal, of course it has to be normal with its mean and its variance. So sample mean has always mean mu and variance sigma square over n, where mu is the population mean and sigma square is the population variance. It just says as n goes to infinity, for IID sample with finite mean and variance, the sample mean becomes normal. And because of this relation between standard normal and general normal, you can modify sample mean to get sample normalized, this normalized object, sample mean minus mu, which is this mean, divided by its standard deviation, not the variance, not sigma square, sigma, and for that sigma will be sigma over square root n. This is normal, this has normal distribution, and because this has normal distribution, this probability can be calculated using the normal probability. So this is standard normal. So we know the the probability density function of standard normal, it can be calculated using that. So basically this probability, because this has standard normal, this probability can be calculated using standard normal. So this just means if this is standard normal, in absolute value the probability of a standard normal being less than this, which means z is, so in absolute value z less than epsilon over square root n by, this means z is inside this interval minus epsilon square root n over sigma, epsilon square root n over sigma, and this is just this integral. But then as you take n going to infinity, this just becomes minus infinity to infinity of this integral. And now for any, so remember, if x has PDF fx, then integral minus infinity to infinity fx dx is equal to 1. This is the probability of a normal random variable being a number, it belonging to whole of real line. So of course it has to belong somewhere, and it's becoming minus infinity to infinity simply because these limits are becoming this is becoming plus infinity, and this is becoming minus infinity as n goes to infinity. So this is a calculation which tells you this is an consistent estimator of population mean. Sample mean is a consistent estimator of population mean. Now also it is true that population sample median is a consistent estimator of population mean for normal population. So sample median is just the middle value. So if if your numbers are 1, 2, 3, 1, 2, the middle value is 2. So basically whatever is if you are not 2 actually, so the sample, so median is just 1, 2. So suppose this is your data, you just organized in increasing order. This is 1, 1, 2, 2, 3. So there are 5 things. The third one will be the middle one. So if there are even number of things, you take the middle 2 and then take their average. So for example, if you have 1, 2, 3, 4, the middle 2 are this, you just take 2.5. So the middle value of the sample. So the sample median is also known to be it's also known, it is actually also an unbiased estimator of population mean for normal distribution. This is something known, and this is also its variance. Here you can check for this, because this is an unbiased estimator asymptotically for every n. This is expected value of this estimator as n goes to infinity is also mu, and the variance from this is showed that this is goes to 0. So due to this sufficient condition we discussed before, this will tell us that sample median for normal population is also a consistent estimator for the population mean. So this condition coupled with this will tell us this is a consistent estimator. Sample variance, if you take the random sample from a population with mu and sigma square, both expressions are called sample variance depending upon the context, but this is generally more widely accepted as this has this unbiasedness property. Estimator of, so basically both of them are consistent estimator of population variance. One can check this is for finite population. So expected value, we check that this is equal to n minus 1 times this s square over n as n goes to infinity, because as n goes to infinity, n minus 1 over n goes to 1. So asymptotically s prime square, expected value of s prime square is population variance. So this is what essentially is happening. So that property is satisfied, and then one has to basically show the variance of this estimator, namely s square goes to 0, and basically one can see that this is actually, this one knows from a fact that this follows chi-square distribution. So if you take expected value, this is happens this. So this is basically chi-square distribution. That also tells you that this expected value goes to sigma square, and variance of this can be calculated from chi-square distribution, which is basically this. The variance comes out to be this. Note that there is n squared in the denominator and n minus 1 in the numerator. So this goes to 0 as n goes to infinity. Again, based on this result, that asymptotically this expected value has to go to theta, and asymptotically variance has to go to 0, then that will imply that the estimator is consistent. This shows that this estimator is a consistent estimator, because this is again chi-square distribution. Expected value of is this, which tells you as n minus 1 over n goes to infinity, this goes to so as n minus 1 over n, as this goes to 1, this whole thing goes to sigma square, and variance is this object, which we can see because this is linear divided by quadratic in n, the variance goes to 0. So this gives you a consistent estimator. The details are there in the notes, you can take a close look. So this is gives you a consistent estimator, and unbiased estimator that is not consistent. This is very interesting. you know, if you take a population of x1, x2, xn, just x1, if you just take just x1, that is also an estimator. Just, you know, just take the first value. Now, this is definitely unbiased because this is from the same population. So, of course, expected value of x1 is mu and expected value of, and the variance of x1 is sigma squared. However, this is not an consistent estimator. So, one can check that, you know, probability of x1 minus mu greater than or equal to sigma, because n1 has, x1 has probability mu sigma squared, this is equal to 1 minus, so probability of this being bigger than epsilon will be 1 minus probability this is being less than or equal to epsilon. But this is a general normal distribution, no n involved. This is a continuous distribution. Whatever this region is, this is non-zero. So, this is for any epsilon greater than 0, this is just, you know, this is your mu. This region has non-zero probability. You can take as small epsilon as you want, does not matter, but for a fixed epsilon, as n goes to infinity, x1 remains the same. So, this remains non-zero. So, this is not an consistent estimator, but this is of course an unbiased estimator because you are drawing the sample from the same population. So, this gives you an example of a consistent estimator that is not unbiased. So, some properties of consistent estimator, I will just quickly wrap up this class. I mean, I think I have given you a glimpse of asymptotics that is involved in point estimation and some nice behaviors that you can expect as the sample gets bigger and bigger. So, consistent estimator may not be unique, of course. I mean, both sample mean and median are shown to be consistent estimator of population mean for normal population, and they need not be unbiased. The estimator S square we just saw, the 1 over n version of the variance, that is not an unbiased estimator. It is consistent but not unbiased estimator. I mean, in general also this result is true that 1 over n summation xi minus x bar whole square is not an unbiased estimator. We saw the proof for the finite sample case, but it is in general also true that this is not unbiased, but nevertheless we saw this is an consistent estimator. An unbiased estimator need not be consistent. Consistent estimator need not be unbiased, unbiased estimator need not be consistent, that we just saw for the estimator for, you know, for the unbiased estimator x1 for population mean. So, consistent estimator has some other properties, is invariance property, that if it is a continuous function of theta, then this is a consistent estimator of f theta. So, for in fact this is very useful because once you establish one consistent estimator for something, you can kind of take composition with various function to get consistent estimator for various other functions of theta. And finally, consistent estimator has some drawbacks. So, shape of the sampling distribution of consistent estimator is of course not known, as the estimators in most cases are nonlinear functions of random sample. Mean is one thing, but variance already you see that is a nonlinear function. So, nonlinearity becomes extremely actually necessary when you are looking for consistent estimator on many things. And even if the sampling distribution of the consistent estimator is known, it will change with sample size, that is another issue. So, you know, consistent estimator essentially is a family of estimators. So, as n goes to infinity, even if the nature is known, even in case of sample mean you have seen, because it is the sample mean is a consistent estimator, but for various n, sample mean has different variance, sigma square n over n, that changes with various n. Finally, consistent asymptotically normal estimator, and estimator is said to be consistent asymptotically normal estimator for parameter if the asymptotic distribution of Tn minus theta over n follows normal 0 sigma square. I think I will stop the talk here. Thank you.